What if we could ride on the back of a beetle and see what it sees? Imagine exploring the world from an insect's point of view, streaming real-time video as it crawls through underbrush, scales rocks, or wanders the forest floor. Sounds like science fiction? Well, it's real. Vision is essential for animals. It helps them find food, avoid predators, communicate, and navigate their environment. But what's truly fascinating is how small animals like insects manage this complex task under extreme constraints. A human's eyes and visual cortex account for about 0.6% of body mass. For insects, their visual systems can take up between 2.5 and 13%, a massive investment of body mass and energy. To make that energy investment worthwhile, evolution took a clever turn. Rather than seeing the entire world in high resolution, many insects concentrate their visual acuity in a small part of the retina. Then, they move their heads to scan, lock onto moving targets, or widen their field of view, allowing them to see more without moving their entire bodies. It's a highly energy-efficient workaround to a tough engineering problem. What happened to insects also applies to robots. Vision is one of the biggest challenges for insect-scale robots. Adding a camera to something the size of a coin isn't just about shrinking the lens. We need to power it, process the data, and transmit it wirelessly. And all of that has to fit on something that weighs less than a gram, ideally less than 500 milligrams. Let's talk about what's been tried before. Some researchers used smartphone camera modules. They're compact and high resolution, but they demand too much power and require large batteries and processors, not feasible for tiny robots or live insects. Others look to capsule endoscopy systems, those swallowable pill cameras. Better, but they still consume 65 to 115 milliamps and need large, heavy batteries. Some aerial robots, like the 10-centimeter Delphi Micro, manage to fly with a wireless camera, but the camera system alone weighs over a gram and guzzles 200 milliwatts. Then there are systems that stream video using low-power backscatter communication. That saves energy, but they only work within a few meters and are too heavy for insects. A few flapping wing robots have managed to carry tiny cameras, but they're tethered to external computers and power sources, so not really free roaming. To tackle the challenges of insect-scale robot vision systems, a team from the University of Washington has developed a miniature, wireless, steerable vision system that mimics insect head motion. It's light enough to ride on the back of a beetle and efficient enough to run for hours on a button-sized battery. And it can pan its view like an insect turning its head, all while streaming video to a smartphone over Bluetooth from up to 120 meters away. This system weighs just 248 milligrams. That includes the camera, the electronics, the actuator, and the battery. The camera itself streams 160 by 120 pixel monochrome video at 1 to 5 frames per second, using only 4.4 to 18 milliwatts of power. But the real magic lies in the steering. Instead of rotating the whole body of a robot or insect to change its view, the system uses a piezoelectric actuator, a type of artificial muscle. It's made of layered ceramics that bend when voltage is applied. The team designed a custom micro-robotic head that translates that tiny bend into a 60-degree pan of the camera. That's the same range of motion seen in real insects like hawk moths and blowflies. Why is this a big deal? Because it's dramatically more efficient. In their tests, moving the camera head instead of the whole robot used up to 84 times less energy. Even better, the actuator can hold its position for over a minute after being powered off, thanks to a clever electrical design with ultra-low leakage components and capacitors. It only uses energy when changing position, not while holding still. To steer the camera, the team built a custom 96 milligram boost converter that steps up the battery voltage to over 200 volts, just enough to charge the piezo actuator. Once set, the actuator holds its angle without drawing power. The vision system consists of an image sensor paired with a Bluetooth chip, with a custom wire antenna handling wireless transmission. Two lightweight lenses, 1.5 millimeters and 3.8 millimeters, were used for close-up and distant views. The full camera module, including its carbon fiber housing, came in at just 24 milligrams. Field tests were done on live beetles. A motion-triggered accelerometer kept the system asleep when idle, extending battery life to 6 hours on just a 10 milliamp hour cell. In one test, A pinnacate beetle carried the full system. When it moved, the camera panned in 15-degree steps, capturing panoramic images of its environment, including nearby buses, just centimeters from the ground. They also built a tiny terrestrial robot, 1.6 by 2 centimeters, that carried the entire system. It used 2 vibration motors and hit speeds of 3.5 centimeters per second, over twice its body length per second. Thanks to the steerable head, the robot could look around without turning, saving 26 to 84 times more energy than body rotation. In final demos, the robot navigated via live video feed and tracked a moving target by rotating its camera head, all with minimal power. It proved that wireless, steerable vision at insect scale isn't just possible, it's practical. This project takes cues directly from nature, low-resolution vision systems that move instead of compute. The entire camera and processing unit use just 4.8% of the total robot mass, well within the range seen in real insects. And the camera worked even in low-light conditions, down to 5 lux, equivalent to twilight. But the current system isn't without trade-offs. First, it's still too heavy for the beetle to carry naturally. Video footage shows reduced speed and limited agility. Second, the video transmission is not truly real-time. Bluetooth bandwidth restricts frame rates to just 1 to 5 frames per second, making the feed choppy and unsuitable for fast reactive tasks. Still, this is a milestone. It shows that insect-scale robots, and even insects themselves, can carry wireless, steerable vision. With smarter hardware and better energy management, we're getting closer to autonomous micro-robots that see and act like living creatures. And who knows, maybe that beetle crawling by is already live streaming. If you're interested in this research, please check out the original paper published in Science Robotics. It's a great example of how bio-inspired design is pushing the boundaries of micro-robotics. You'll find the link to the paper down in the description. And if you're curious about how robotics is transforming the way we study insects and animals, we have more videos on this channel exploring those topics. So, be sure to check those out. If you found this video helpful or inspiring, consider subscribing and let us know in the comments what cross-disciplinary research you'd like us to explore next. Thanks for watching, and see you in the next one.